Hi, everybody. Hope you're doing well these days. I want to get going through chapter 16. Okay, so chapter 16 is related to chapter 15 because chapter 16 is all about solutions. Obviously, we started talking about solutions in chapter 15. We talked about the properties of water, and we talked about dissolving stuff in water. And then we talked about different kinds of mixtures in water, like suspensions and colloids and solutions. And now we're going to just focus on solutions. In fact, really the rest of the way through the rest of April and the rest of May is just talking about solutions, right? That's our main focus, since a lot of things in chemistry deal with solutions, okay? So a solution, let's just review for a moment here. A solution is a homogeneous mixture, okay? Any kind of homogeneous mixture. That just means that it's evenly mixed and something is dissolved in something else. It could be solids, liquids, gases, it doesn't matter. Now, most of the time, like we kind of said back in chapter 15, most of the time the solutions that we talk about in this class are a solid that is dissolved in a liquid. And the liquid, the solvent, is usually water, right? So here's our typical solution that we would talk about in here. We've got a solvent, again, like I said, usually water, but it doesn't have to be. And then we have a solute. And remember, the solute is the thing that's being dissolved, and then the solvent is the thing that's doing the dissolving. Okay, so let's just imagine again this process of solvation, right? The process of solvation is the process of the solvent actually surrounding the solute and attracting to it. So let's imagine that we're dissolving salt, sodium chloride table salt, in water, right? What would it look like is happening in those spots? All right, if you see in these pictures here, you've got NaCl, but of course NaCl salt is made up of two ions, Na positives and Cl negatives. Na positives would of course be attracted then to any negatives that are out there. Well, water is polar. It has a partially positive end and a partially negative end. So the partially negative end is going to be attracted to the Na positives. And you notice all of those little water molecules, all those little Mickey Mouse heads that are there, those are water molecules. They're all attracted to the Na positives because the negative end of the water molecule, which is the oxygen end, is partially negative. Negatives and positives attract. Well, the Cl negative, the other ion in salt, is also going to be attracted by water. So the water molecule's positive ends, those would be the hydrogen ends of water, are going to be attracted to the Cl negative. And you notice how water then surrounds both of those ions. So all of that salt that you would dump into the water is slowly, ion by ion, being surrounded and taken away and separated to the point where the water is now going to be evenly attracted to all the Na positives and all the Cl negatives, and suddenly they're down to their ions and you can't see them anymore, right? That's what the process of solvation is called. So what factors affect how fast this would go, okay? So we call this the rate of solution formation or the rate of dissolution. So how fast could you get something to dissolve depends on a few factors. One of those factors is, what are you dissolving? It depends on what solvent and solute you pair together. If you remember, solutions only form when one is like the other, right? Salt dissolves in water because water molecules are polar, right? They have a positive and negative end, and salt is ionic, so it obviously has a positive and a negative ion in it. So the positives and negatives of both of those things can attract to each other. Therefore, salt and water can dissolve. Oil, however, if you put oil in water, oil doesn't dissolve in water because oil is nonpolar. Water is polar. Oil is nonpolar. That means it doesn't have any positives and negatives to it. There's no reason why water and oil would ever attract to each other. And that's why when you try to mix them together, they stay apart. So this is where we got our term, that little phrase from the last chapter, like dissolves like. Right? Polar dissolves polar, nonpolar dissolves nonpolar, but you can't have two opposites. Okay, you can't have nonpolar and polar, for instance. Now, what are some other factors that affect how fast? Once you find something that actually dissolves, then we have to talk about things like temperature, right? If you increase the temperature of something, that means that all of the little particles are going to start to move faster. That's what temperature is really a measure of, right? It's a measure of kinetic energy, which is how fast things are moving. So if you increase the temperature, let's say, of the water that you're dissolving something in, well, if the water molecules are moving faster, then they should be able to go around and attract and collide with all of the other particles that they're dissolving much faster. Therefore, you should dissolve faster. So increasing temperature means that you will increase the rate at which something dissolves. What's another thing that we can do to increase the rate at which something dissolves? Well, we can increase the particle size, or decrease, I should say. If we split some kind of larger chunk into smaller chunks, right, into smaller pieces, there's more surface area. So imagine if you were trying to dissolve salt in water. I could, if I really wanted to, I could find salt out there that comes in really big chunks. We're used to salt being ground up into tiny little particles so that we can shake it in our French fries and stuff like that. But salt could be in very large crystals. And if you tried to put one really large crystal into water, it would still dissolve, but it would take a lot longer. Because the only part of the actual salt cube that could come in contact with the water is just the outside of it, right? So imagine if the water wanted to try to dissolve this chunk of salt, it could attack it here, right? Or here, or here, but it could never get to the middle of that until the outside had been dissolved first. Or what if we took this big chunk, right, and we broke it down into a bunch of smaller pieces? If we break it down into a bunch of smaller pieces, notice that the water molecules can get in between all of these. And the water can now find its way to all of those places that were kind of locked up before in the middle of that bigger chunk. So if we increase the surface area, we will increase how fast something will dissolve. This is usually why you find that salt and sugar and things that we like to dissolve in our water, coffee, tea, right? All of these things are usually ground up into tiny little particles because they will dissolve faster that way, right? We don't do that just because we like the looks of salt that way. We do that simply because it dissolves faster, right? And then the last thing that goes along with this is something we would call agitation. You've probably heard this word before, right? Agitation is the stirring or shaking or in some way disturbing it. So again, if I wanted to dissolve salt in water, if I just dumped the salt in the water and I just let it sit there, eventually all the salt will dissolve. Eventually, but it would take a while because you're not stirring it, you're not shaking it up, you're not agitating it. If you agitate it, more water can come in contact with more of the solute, and therefore more of it can dissolve faster. Now look at these three. these three factors, these are the three main factors. I know we had one before, but once we find out something that dissolves in water, then there's three different ways that we can increase how fast it dissolves. Now I want you to think of this in terms of, let's say, something you're probably familiar with, like coffee. I know a lot of you drink coffee, okay? You know how coffee is made, right? There are some very, very basic things that you need to make coffee. You need water, and you need coffee beans. You technically need nothing else, right? If you just took some whole coffee beans, you've probably seen these before in your life, either a picture of them or in real life you've seen whole coffee beans. If you just took whole coffee beans and they were dumped into some water and just sat there, cold water, no stirring, nothing else, you would eventually still get coffee that you could drink. I don't know how tasty it would be, and it certainly would take a long time for it to get to any kind of strength that anybody would care for, but it would happen. So what do we usually do with our coffee? Well, let's look at our three factors. Temperature. We usually make our coffee hot. Even if you like iced coffee, they don't make it cold to begin with usually. They make it hot and they put ice in it to cool it down. So why do they make it hot? Because it makes it faster to dissolve the coffee into the water. Particle size. What do we usually do with those beans? We usually grind them up into smaller pieces. Why? Not because we like to, but because it makes the whole process go faster. You have smaller chunks, more of the water, more surface area can get exposed to that water, and it can dissolve faster. And the last thing, agitation. Think about it. If you're making coffee, you're probably using a coffee maker. If you have a coffee maker going, the water isn't standing still the whole time. The water's constantly moving through that machine, getting pumped from here to there and going through something. It's agitating. It's moving along the way because it makes it go faster. This is why we do this. Same thing happens for tea. If you're a tea drinker, you're like, oh, I like hot tea or I like iced tea. Well, again, the same thing happens. What do they have to do to make tea? You usually make it in hot water. Even if you make iced tea, you usually make it in hot water first. The tea leaves are usually ground up and put into a little bag, right? And then it's usually agitated, stirred, or something happens to it. Okay. This is the reason why we do these things. Most people don't think of it. They're like, well, that's just how you make coffee. I don't know why they do it. Well, this is why they do it. Now, this works for any solution, okay? It doesn't matter if it's... All right, so again, factors affecting solubility, not how fast, but how much dissolves. So temperature. Again, temperature not only affects how fast something dissolves, but affects how much. If you increase the temperature of a solvent, the solubility of that solid solute, will increase. So how much you can get dissolved increases. So if you were to make the water hotter and hotter, you would get more and more of the solute to dissolve in it. As long as the solid or the solute is a solid, this works. If you do it for a gas, it's just the opposite, right? It's a little bit strange. If you look at the solubility of a gas as the temperature goes up, the solubility actually goes down. Look at this, carbon dioxide's solubility or oxygen's solubility in water goes down. Now I want you to think about this for a minute. What purpose would you have for putting carbon dioxide in water? Right? You actually probably come in contact with this a lot in your life, especially if you like carbonated beverages, right? That's what a carbonated beverage is all about, like pop, right? Any kind of seltzer kind of water where there's bubbles in the water, that's carbon dioxide. Now, carbon dioxide, as we know it, is nonpolar, right? If we were to draw the Lewis structure for carbon dioxide looks like this. Okay? This is a little bit of review. Right? And carbon dioxide has an electronegativity difference. So the oxygen is more electronegative than the carbon is. So the carbon gets electrons pulled away from it, so it becomes partially positive. And the oxygens are partially negative. Now, look at this. This end of the molecule is negative. This end of the molecule is negative. That means the entire carbon dioxide molecule is nonpolar. Now, we just learned a few moments ago that nonpolar doesn't dissolve in polar. So carbon dioxide gas should not be able to dissolve into water, right? Because we know water is polar, right? Water looks like this. And the oxygen's partially negative, and those hydrogens are partially positive. And that means that we have a positive end of the molecule, we have a negative end of the molecule. So water is polar. Now, those two have no reasons to attract to each other. Okay? There's no reason for water and carbon dioxide to really attract to each other. One's nonpolar, one's polar. But you can force the carbon dioxide to go into the water if you do so at high pressures. So if you push the carbon dioxide into the water, you can force it to go into the water. But if you make the water molecules move really fast, the carbon dioxide won't be able to stay in that water because there's nothing holding it in the water. So if we wanted to make pop, we wanted to make carbonated water, you would need to make sure that your water is colder, right? The colder the water is, the less it's moving around, the easier it is for you to force these carbon dioxide molecules that don't have any attraction for the water at all to stay in the water. But solids do better when the solvent is moving around more. So if the temperature goes up, the solubility of a solid increases, but if the temperature of the solvent goes up, the solubility of a gas decreases. And then of course we have pressure, we just talked about this. So as the pressure of a gas increases, the solubility of a gas increases. So if you put a lot of pressure on that gas, you can get a lot more of it to dissolve. So if you're making pop, you're the Coca-Cola company or whatever, right? And you want to make sure that your Coca-Cola has all the carbon dioxide dissolved in it that people like to have. They like to have all those bubbles in it. How do you get the carbon dioxide to stay in there? Well, first of all, you'd have to do it under high pressure. This is why when you open up a can of pop or a bottle of pop, you hear that hiss, because that's all of that pressure that's escaping. And we usually store our pop cold, right? Why? Because again, that means that all of that carbon dioxide will stay dissolved in the water and won't come out. Because if all the carbon dioxide comes out, there's no more bubbles, and we call that flat pop, and most people don't like flat pop. If you like flat pop, you might as well like just Kool-Aid. That's all it is. It's just sugar water. Most people like sugar water with bubbles. Okay. All right, what you see here is something that comes up a lot in chemistry, and I want you to be familiar with how to read this. This is called a solubility curve. All right, a solubility curve just simply shows us what is the solubility, how much can dissolve of a substance at different temperatures. And you can see there are several different substances that have solubility curves on this graph. So there's some questions. I want you to be able to look at this, and then I want you to be able to answer some questions. So let's just do some examples. What happens to the solubility of KNO3 as the temperature increases? All right, so you can see where KNO3 is on this graph. Right, the KNO3 line is going up on this graph. So what happens to the solubility as the temperature goes up? The solubility goes up, right? So KNO3 is like most other solids. The solubility goes up when the temperature goes up. Which substance exhibits the least change in solubility as temperature increases? So look at all these curves. Which one changes the least as the temperature goes up? Well, that would be the NaCl, right? The NaCl looks like it's almost a flat line. Now, it's not exactly flat. It does go up a little bit, right? But not much. Suppose you added some solid NaCl to a saturated solution of NaCl at 20 degrees Celsius, and then you warmed the mixture to 40 degrees Celsius. What would happen to the added NaCl? Well, that's a lot to break down here, so let's take it word by word. First of all, it said that we're taking solid NaCl and we're making a saturated solution. Now, remember what saturated means, right? Saturated means that it's holding all of the possible that it can hold. So let's look on this graph. Let's see where that would be. So NaCl at 20 degrees Celsius would be right in here, right? Okay. So at that point, it would be what? Let's call that 38 grams in 100 grams of water. I think that's about what that would be. So at 20 degrees Celsius, if I had all of the possible NaCl that could dissolve, it would be 38 grams in that 100 grams of water. Now, let's say that I added some solid to something that was already saturated. So if I had a saturated solution with 38 grams of NaCl in it, and then I added some more solid NaCl to it. Well, at 20 degrees Celsius, if we're at saturation, we're not going to have any more dissolve. I don't care how much you stir it. Nothing else is going to happen. If I have 100 grams of water and it's 20 degrees Celsius, this is the maximum amount that can dissolve. So if I put more solid in there, that's not going to dissolve. However, if I warm it up to 40 degrees Celsius, now I know this line, again, like I just said, looks like it's flat, but this line does go up slightly. So let's say that the solubility at 20 degrees Celsius was 38 grams. Now it's up to 38.5 grams. What would happen to some of that solid NaCl now that was just sitting there? Well, now some of it would start to dissolve, right? Because there's more room when you heat up the solvent, there's more room for more solid to dissolve. All right, last question. How do you think the solubility of KCl changes as the temperature decreases? All right, so again, look at this. I want you to find, how would you answer that? Well, if you're looking at that, you're like, wait a minute. KCl is not on this graph. Is that a typo? It's not a typo. They meant to say KCl, but it's not on that graph. So how could you answer a question about KCl when the graph doesn't have KCl on it? Well, think about it. Out of all the things that are there, do you have something that's similar to KCl? Don't you think NaCl should be similar to KCl? Or don't you think that KBr would be similar to KCl? So those seem to be like really similar compounds. And so let's read this and substitute in NaCl or KBr in for this and see how we would answer this. It says, how does the solubility change as the temperature decreases? So as you go down in temperature, what happens to the solubility of both of those? Their solubility goes down, doesn't it? So KCl is probably going to be really similar to KBr or NaCl. Therefore, we expect KCl to have its solubility go down when the temperature goes down, because KBr and NaCl do the same thing. Right? It's using a little deductive reasoning when you're looking at this. All right. The kind of final thing that I want to mention here is that we talked about a solution that's saturated, meaning it's holding all that it could possibly hold. But there are solutions that can be super saturated, right, where it carries more solute than it can normally have at a given temperature. Now, these don't happen very often. It's kind of rare, but you can make a supersaturated solution. If you were to heat up some water, let's say, and you were to dissolve something at a really high temperature, and then you were to slowly let that water cool off, you can sometimes trick the water into holding more of that solid than it should be able to when it cools off. And we can make a super saturated solution, right? So it can only be created under very specific circumstances. And of course, all the extra solute that's there should precipitate out, should come back out as a solid when it cools down, but it doesn't always happen. Right? All right, and then the very last thing, we're talking about the solubility of gases a little bit here. There is a law that goes along with the solubility of gases. It's called Henry's law. Right? And Henry's law works like this. S1 divided by P1 equals S2 divided by P2. The S's stand for solubility. That's the solubility of the gas, and P stands for the pressure. So this tells you that the solubility of a gas goes up when the pressure goes up. Right? That's all this is saying in a mathematical form. Right? The solubility of a gas is proportional to the pressure of the gas. Okay, that's what this means. So if I record what the solubility of a gas is at one pressure, and then I set it equal to the solubility of the gas at a different pressure, they should be equal to each other when I divide them. So let's try a little bit of an example of this. If the problem says 0.55 grams of a gas dissolves in 1 liter of water at 20 kilopascals of pressure, how much will dissolve at 110 kilopascals of pressure? Well, we have to do a few things to solve this problem. One of the things we have to do is write down our knowns and unknowns. So let's write down what we know from this problem. First thing I know is the solubility of the gas. They told me at the beginning that 0.55 grams of the gas dissolves in 1 liter of water. So that's 0.55 grams per liter. I also know what the first pressure was. It dissolved originally at 20 kilopascals of pressure. I also know what the second pressure is. The second pressure is 110 kilopascals of pressure. So what's the one letter, what's the one variable that we haven't talked about yet that's in that formula? S2. So what's the unknown? It's asking for what is the new solubility? How much will dissolve at this new pressure? So we're going to set up our equation. Our equation is Henry's law, S1 over P1 equals S2 over P2. And now we're just going to substitute in the numbers. So what's S1? It's 0.55. What's P1? It's 20. What's S2? I don't know. What's P2? 110. And you notice when we set this up, if we want to get S2 by itself, there's a number of different ways we could do this. Okay. We could take 0.55, we could divide it by 20, and then we could multiply the 110 over, or we could cross multiply here. We could take 0.55 times 110 equals S2 times 20. And then you'd have to divide the 20 out. So there's multiple ways you could solve this to get S2 by itself. You have to do just a little bit of algebra here to solve for S2. So I want you to take a moment, take your calculator out. I want you to go through and solve this. Pause it for a moment, solve this, and then I'll put the answer up. Okay, so you solve this, you figure out what S2 is. You should have gotten an answer of 3.0. It has to be 2 sig figs because the least number of sig figs in my problem was 0.55. That was 2 sig figs, so my answer has to be 2. So 3.0 is my answer, and then I have to have the same units I started with. I started with grams per liter. I have to end with grams per liter. And don't forget to circle your final answer. All right. Okay, so again, a few things that we covered here. Right? We covered things like solubility. We covered the factors that affect how fast something dissolves. And all of this relates back to solutions. We have a couple other things that we're going to cover on Friday. We'll do some review on Monday then next week. And then Wednesday of next week is when your homework problems for chapters 15 and 16 will be due. Okay? If you've got any questions about any of this stuff, again, please let me know so that you don't get confused and you don't get behind, and we can cover it and go from there. Okay? All right. Stay healthy and happy.